Okay, so for the first question, we're given that y is equal to 3 sin theta over 2 sin theta plus 2 cos theta, and we need to show that dy over d theta is equal to a over 1 plus sin 2 theta, where a is a rational constant to be found for 5 marks. Okay, so if you don't know, I've made videos on all of the Edexcel A-level maths syllabus, and any videos that are relevant for particular questions, I will link them in the description. Now, as we have to differentiate this function here, and this is a fraction, we need to use the quotient rule here. Now, I've given you the formula for the quotient rule here because this is given to you in the formula booklet, so you'll have access to it in the exam. So we're differentiating this f of x over g of x. So if we apply this to this function here, so the function in the numerator is going to be the f of x. So in this case, because we don't have x, we have theta, it's technically going to be f theta, like this here. And then the function in the denominator is going to be the g theta, like this here. Okay, so we have the f theta is equal to 3 sin theta, and g theta is equal to 2 sin theta plus 2 cos theta. Now, to use the quotient rule, we need f dash of theta and g dash of theta. So if we differentiate both of these, so f dash of theta is going to be 3, and if you differentiate sin theta, it's cos theta, and then g dash of theta is going to be 2, and if you differentiate sin theta, it's equal to cos theta, and then this is plus 2, and if you differentiate cos theta, it's equal to minus sin theta, so this is going to be minus 2 sin theta, like this here. So we have f theta, f dash theta, g theta, and g dash theta. So we can sub them into this equation here. So if we do this, so it's going to be dy over d theta is equal to, so it's going to be f dash of theta, so this is 3 cos theta, multiplied by g theta, which is 2 sin theta plus 2 cos theta, and then this is minus f theta here, so this is 3 sin theta multiplied by g dash of theta, so this is the 2 cos theta minus 2 sin theta, and all of this is over g theta squared, so this is going to be 2 sin theta plus 2 cos theta squared, like this here. Okay, so we need to show that dy over d theta can be written in this format here. Okay, so firstly, let's expand all of the brackets here. So if we do this, so firstly, this 3 cos theta times 2 sin theta is going to be 6 sin theta cos theta, and then this is going to be plus, and then 3 cos theta times 2 cos theta is going to be 6 cos squared theta, and then this is going to be minus, and then 3 sin theta times 2 cos theta is going to be 6 sin theta cos theta, and then 3 sin theta, or sorry, minus 3 sin theta multiplied by minus 2 sin theta is going to be plus 6 sin squared theta, like this here, and all of this is over this here squared, so it's going to be 2 sin theta times 2 sin theta, which is 4 sin squared theta, and then this is plus 2 sin theta times 2 cos theta, which is going to be 4 sin theta cos theta, but remember this is going to recur twice, so it's going to be 8 sin theta cos theta, and then it's going to be 2 cos theta times 2 cos theta, which is 4 cos squared theta, like this here. Okay, so we can do some simplifying on this. So firstly, here we have 6 sin theta cos theta minus 6 sin theta cos theta, so this and this will cancel out. So in the numerator we're just going to be left with 6 cos squared theta plus 6 sin squared theta. Then in the denominator, I'm going to rewrite this slightly. I'm going to rewrite this as 4 sin squared theta. I'm going to bring this 4 cos squared theta here, so it's going to be 4 cos squared theta plus 8 sin theta cos theta. Now, if you remember the trigonometric identity that sin squared theta plus cos squared theta is equivalent to 1, well, you can see that we have this twice here. We have it in the numerator here. We have 6 cos squared theta plus 6 sin squared theta. Now, as we have 6 in front of both the terms, and as sin squared theta plus cos squared theta is equivalent to 1, this here is going to be equal to 6 in the numerator, and then in the denominator here we have 4 sin squared theta plus 4 cos squared theta, so this is going to be equivalent to 4, like this here, and then plus 8 sin theta cos theta. Now we need to show that dy over d theta is equal to a over 1 plus sin 2 theta. Now remember the double angle formula, that sin 2 theta is equivalent to sin theta cos theta. So here we have 8 sin theta cos theta. So if we multiply everything here by 4, so on this side it's going to be 4 sin 2 theta, and this is equivalent to 8 sin theta cos theta, which is what we have here. So what we can do is we can sub this out, so we can write this as 6 over 4 plus, and then instead of 8 sin theta cos theta, we can write 4 sin 2 theta. Now again, if you look at the final answer, we need in the denominator this 1 plus sin 2 theta. Now here we have this 4 plus 4 sin 2 theta. So if we factorise out 4 from this, it's going to be 4 1 plus sin 2 theta, like this here, and this is under 6, and then if we bring this 4 into the numerator, it's going to be 6 over 4 over 1 plus sin 2 theta, and 6 over 4 is 3 over 2, and then 1 plus sin 2 theta, like this here, and this here is in the correct format where a is equal to 3 over 2, and this here is the final answer. Okay, so for the second question, we're given that y is equal to x, 2x plus 1 to the power of 4, and we need to show that dy over dx is equal to 2x plus 1 to the power of n multiplied by ax plus b, and we need to find what n, a, and b are for 4 marks. So we need to differentiate this here. So to differentiate this, because we've got these two terms, x and 2x plus 1 to the power of 4 multiplied together, we're going to use the product rule. Now, as we have this 2x plus 1 to the power of 4, which is a bit more complicated to differentiate, we're going to use the version of the product rule where we call one of the functions u and the other one v. So let's say that u is equal to x, and let's say that this 2x plus 1 to the power of 4 is v. So if you remember the product rule, if we're trying to differentiate uv, this is equal to u dv over dx plus v du over dx, like this here. So u is x and v is 2x plus 1 to the power of 4. So if we find du over dx, if we differentiate x, this is just equal to 1. And then if we find dv over dx, so we differentiate this 2x plus 1 to the power of 4. Now to differentiate this, we need to use the chain rule. Now there's lots of different ways that people teach and do the chain rule. The way that I taught the chain rule is that the chain rule is equal to the inner function differentiated, and this is multiplied by the outer function differentiated. So what I mean by this, so let's take the 2x plus 1 to the power of 4 as an example. So we have 2x plus 1 to the power of 4. The inner function is the function inside the bracket, so this is this 2x plus 1, so this is the inner function, and the outer function is this power of 4 here, so this is the outer function. So the chain rule is the inner function differentiated. So this is this 2x plus 1 differentiated. If we differentiate 2x plus 1, if you differentiate 2x, this is equal to 2, and if you differentiate 1, it's just a constant, so it just goes away. So the inner function differentiated is 2, and then this is multiplied by the outer function differentiated, which is this power of 4 differentiated. Treat this like x to the power of 4. So if you differentiate x to the power of 4, the 4 comes down as a coefficient, so this is going to be 4 like this here. Now when we differentiate the outer function, we don't touch the inner function, we just keep this as 2x plus 1 like this here, and then if we're differentiating a power of 4, it's going to go down to a power of 3 like this here, and then we can simplify this because we have 2 times 4, which is 8, so it's going to be 8 2x plus 1 to the power of 3. So this is dv over dx. So therefore, if we use the formula for the product rule, it's going to be, so this is going to be dy over dx is equal to u, which is x, and this is multiplied by dv over dx, which is this 8 2x plus 1 to the power of 3, and this is plus v, which is this 2x plus 1 to the power of 4, and this is multiplied by du over dx, which is 1 like this here. Okay, so we need to simplify this here, and we need to write it in this format here. So firstly, let's just simplify this. So we have this x times this 8 2x plus 1 to the power of 3, which is going to be 8x 2x plus 1 to the power of 3. Then this is plus 2x plus 1 to the power of 4 times 1, which is going to be 2x plus 1 to the power of 4. Now we need to write this in the format where we have this 2x plus 1 to the power of n factorised out. Now if you look at these two terms here, we can factorise out 2x plus 1 to the power of 3 from both of these terms here. So if we do this, so it's going to be 2x plus 1 to the power of 3. If we factorise out 2x plus 1 to the power of 3 from this term here, we're just going to be left with 8x, and if we factorise out 2x plus 1 to the power of 3 from 2x plus 1 to the power of 4, we're going to be left with 2x plus 1 like this here. Then this is equal to 2x plus 1 to the power of 3, and then we have 8x plus 2x, which is 10x, and then plus 1 like this here, and this is in this format here where n is 3, a is 10, and b is 1, and this here is the final answer. Okay, so for the third question, we're told that y is equal to 5x squared plus 10x over x plus 1 squared. And for part A, we need to show that dy over dx is equal to a over x plus 1 to the power of n, and we need to find what a and n are for 4 marks. Okay, so we need to differentiate this here, and to differentiate this again, because it's a fraction, we're going to use the quotient rule. Again, I've given you the formula for the quotient rule here. So what we're going to say is the function in the numerator is fx and the function in the denominator is gx. So therefore fx is equal to 5x squared plus 10x, and gx is equal to x plus 1 to the power of 2. So we need to get f dash of x and g dash of x. So we start with f dash of x. This is going to be equal to 5 multiplied by, and if you differentiate x squared, it's equal to 2x, and then if you differentiate 10x, it's equal to 10 like this here, and then 5 times 2 is 10, so this is going to be 10x plus 10 like this here. And then if we find g dash of x, so we need to differentiate x plus 1 to the power of 2, so again we need to use the chain rule. So remember, it's the inner function differentiated multiplied by the outer function differentiated. So in the case of x plus 1 to the power of 2, the inner function is this x plus 1 inside the bracket. This is the inner function, and the outer function is this power of 2 here, so therefore if we differentiate this, it's going to be the inner function differentiated, so x plus 1 differentiated. If you differentiate x, it's equal to 1. If you differentiate 1, it's just a constant, so it just goes away. So it's going to be 1 multiplied by the outer function differentiated, so this power of 2 differentiated. Treat this like x squared, so the 2 will come down as a coefficient, so it's going to be 2. Again, we don't touch the x plus 1, we just keep this, we don't differentiate it, and then it's going to be the power, so we're differentiating 2 is now going to be to the power of 1 like this here, and then we can simplify this because we have got 1 times 2, which is just equal to 2, and then x plus 1 like this here, so this is g dash of x. So therefore if we use the quotient rule here, so therefore it's going to be dy over dx is equal to f dash of x, which is equal to 10x plus 10 multiplied by gx, which is equal to x plus 1 squared, minus f of x, which is equal to 5x squared plus 10x, and this is multiplied by g dash of x, which is equal to 2, then this x plus 1 like this here, and all of this is over gx squared, which is going to be x plus 1 to the power of 2 squared, which is going to be x plus 1 to the power of 4, like this here, okay? So we need to show that this here can be written in the format of a over x plus 1 to the power of n. So we need to simplify this. Okay, so if we do this, okay, so firstly, we have this x plus 1 to the power of 2 here, we have this x plus 1 here, and we have this x plus 1 to the power of 4 here. So we can do some cancelling out here, because what we can do is this x plus 1 will cancel out, this x plus 1 to the power of 2 will cancel out once and leave us with x plus 1 to the power of 1, and one of these x plus 1s will cancel out down here and leave us with the power of 3. So we can rewrite this here as 10x plus 10 multiplied by x plus 1, and then this is going to be minus, and now we've got rid of this x plus 1, we still have this 2 here. If we bring this to the front like this, it's going to be 2, then 5x squared plus 10x like this here, and all of this is now over x plus 1 to the power of 3. If we expand everything on the top here, so if we start with this here, so it's going to be 10x times x, which is going to be 10x squared, and then 10 times x, which is going to be 10x, and then 10x times 1, which is going to be 10x, and 10 times 1, which is plus 10 like this here, and then it's going to be minus 2 times 5x squared, which is going to be 10x squared, and 2, so it's going to be minus 2 times 10x, which is going to be minus 20x like this here. All of this is over x plus 1 to the power of 3. And we can do some more simplifying here, because in the numerator, so we have this 10x squared minus 10x squared, so this and this will cancel out, and here we have 10x plus 10x, which is 20x, and we have this minus 20x here, so this will cancel out as well. So we're all going to be left with 10 over x plus 1 to the power of 3, and this is in the format that they're asking for here, where a is 10 and n is 3. So this here is the final answer. Okay, and then for part B, for 1 mark, we need to deduce the range of values of x for which dy over dx is less than 0. And as we found in part A that dy over dx is equal to this here, what we can say is that 10 over x plus 1 to the power of 3 is less than 0, and we need to find the values of x for which this is true here. Now be careful with this inequality. Don't try and treat this like an equation where you're going to try and multiply both sides by the denominator x plus 1 to the power of 3. You can't do that because this kind of 0 complicates it a tiny bit. The way that we can do this is if we consider this, so we have 10 divided by this is less than 0. So if you have 10 divided by something is less than 0, so it's going to be a negative number. As 10 is a positive number, in order for 10 divided by something to be a negative number, this denominator here needs to be negative, okay? So therefore, in order for 10 divided by something to be negative, this denominator here x plus 1 to the power of 3 needs to be negative, so it needs to be less than 0. And we can work with this here. If we cube root both sides, we get x plus 1 is less than 0, and move this plus 1 to the other side, so we get that x is less than minus 1. And this here is the answer. The range of values of x for which dy over dx is less than 0 is where x is less than minus 1. Okay, so here's the fourth question. If you're having a go at these questions yourself, I've given you the formula, the small angle approximation for sin theta for part BI, because you'll need it, and it's given to you in the formula booklet, so you have access to it in the exam. So for this question, we're told that the curve C in the standard Cartesian plane is defined by this equation here, where x is equal to 4 sin 2y, and we're told the curve C passes through the origin O. For part A, we need to find the value of dy over dx at the origin for 2 marks. Okay, so for this here, rather than trying to rearrange this to make y the subject and then differentiating this to get dy over dx, so remember the origin is the point 0, 0. So as well as knowing that x is equal to 0 at this point, we also know that y is equal to 0. So rather than doing what I just said, where we have to rearrange in order to make y the subject, what we could do instead is differentiate this here in order to get dx over dy. And remember that dy over dx is equal to 1 divided by dx over dy. We could do it this way in order to get dy over dx and then get a function involving y, and then subbing in y is equal to 0 in order to find dy over dx. Okay, so if we do this, so if we start by differentiating this here, so this x is equal to 4 sin 2y, so it's going to be dx over dy if we differentiate it in terms of y is going to be equal to 4 times, and then if you differentiate sin 2y, so this 2 is going to come to the front of the trigonometric function like this, and if you differentiate sin, it's equal to cos, so it's going to be 2 cos like this here, and then 2y, so therefore dx over dy is equal to 4 times 2, which is 8 cos 2y. So dy over dx is equal to 1 divided by dx over dy. So therefore dy over dx is equal to 1 divided by this 8 cos of 2y. So it's going to be 1 over 8 cos of 2y. So we know dy over dx in terms of y, so therefore we can sub in the value that y is equal to 0. So therefore dy over dx is equal to 8 cos of 2, and then we sub in 0, and this is under 1 like this here, so therefore dy over dx is going to be equal to, so this is going to be cos 0, and cos 0 is 1, so this is going to be 8 times 1 in the denominator, which is 8, so this is going to be 1 over 8. So this is the value of dy over dx at the origin. Okay, and then for the first part of B, we need to use the small angle approximation for sin 2y to find an equation linking x and y for points close to the origin. Okay, so we have this equation that links x and y. X is equal to 4 sin of 2y. So if points are close to the origin, that means that x and y are going to be small, so therefore we can use small angle approximations. So as sin theta is approximately equal to theta, as we're talking about sin 2y here, this is going to be approximately equal to 2y. So we can sub this in using small angle approximations for sin 2y. So we can write this as x is equal to 4, and then instead of sin 2y here, it's going to be 2y. So therefore x is equal to 8y. So this is an equation linking x and y for points close to the origin, and we use small angle approximations. Okay, and then for the second part of B, we need to explain the relationship between the answers to A and BI. Okay, so this is only worth 1 mark, so it's not the end of the world, but I think there are some students that might struggle with this and might not quite get this relationship. So in part A, we found the value of dy over dx at the origin, and we found it to be 1 over 8. Okay, so in part A, we found that dy over dx is equal to 1 over 8 at the origin. And then in part BI, we found We needed to find an equation that linked x and y for points that are close to the origin, and we found it to be this x is equal to 8y. If we get this in the form y is equal to mx plus c for a straight line, so if you divide both sides by 8 here, we get y is equal to 1 over 8x here. So the gradient here is equal to 1 over 8, which is the same as the value for dy over dx here. This is equal to 1 over 8. Remember that dy over dx is the gradient. So the gradient is equal to 1 over 8 at the origin, which is the same as this gradient here. So we can say that the gradient, which is dy over dx at the origin, is the same as the gradients for the line in part BI. And this would give you the mark. Now, this kind of makes sense, this relationship, because remember that this line here in part BI, it's an equation that links x and y for points close to the origin. So it makes sense that this line has the same gradient as the gradient at the origin for this curve C. Okay, and then for part C, we need to show that for all of the points lying on C, dy over dx is equal to 1 over a and then the square root of b minus x squared, where a and b are constants to be found for 3 marks, okay? So in part A, we found dy over dx, but we found it in terms of y here. Now we need to find it in terms of x. Now, there are actually 2 ways that you can do this question. The way that I would personally do it is here we have this x is equal to 4 sin of 2y. If we divide both sides by 4 here, so we get x over 4 is equal to sin 2y, and then if we take the inverse sin, so this is going to be arc sin of x over 4 is equal to 2y, and then if we divide both sides by 2, we get that y is equal to a half arc sin of x over 4. And me personally, I would differentiate this in order to get dy over dx in terms of x. We can differentiate this using the chain rule, and we talked about how to differentiate arc sin. We talked about it in the differentiating trigonometric functions video. Now, this is the way that I would do it, but the mark scheme suggests an alternative way to do it that I think the majority of people would probably prefer, rather than kind of differentiating this quite difficult function here. The way the mark scheme suggests to do it is, so in part A we figured out that dy over dx is equal to 1 over 8 cos of 2y, and I've written this down here, and we're also told that x is equal to 4 sin of 2y in the question. So this dy over dx, we need to write this in terms of x, but at the moment it's written in terms of y. This here, if we divide both sides by 4, so we get x over 4 is equal to sin of 2y. If you remember the trigonometric identity, that sin squared x plus cos squared x is equivalent to 1. Now here we have sin of 2y and cos of 2y, so if we sub out this x here for 2y, so it's going to be sin squared of 2y plus cos squared of 2y is equivalent to 1. Now we want to sub out this cos 2y here for x terms, and we know that sin 2y is equal to x over 4, so we can rewrite this equation here. Rather than having this sin 2y here, we can sub in this x over 4, so therefore it's going to be x over 4 squared, because it's sin 2y squared here, and here we have sin of 2y, x over 4 squared plus cos squared of 2y is equal to 1. Now we want to sub out this cos 2y, so what we're going to do is we're going to make cos 2y here the subject. So if we move this x over 4 squared onto the other side, we get cos squared of 2y is equal to 1 minus x over 4 squared, like this here. And if you take the square root of both sides, you get cos 2y is equal to the square root of 1 minus x over 4 squared, like this here. And here we have cos 2y as the subject, so therefore we can sub this in for this cos 2y here. So if we do this, this is going to be dy over dx is equal to 1 over 8, and then instead of this cos 2y here, it's going to be this square root of 1 minus x over 4 squared, like this here. And we have dy over dx in terms of x. Now we need to write it in this format here, where in the denominator we have this a and square root of b minus x squared. Okay, so to get it into this format, so firstly we have this x over 4 squared. So if we expand this to get rid of this power of 2, so this is going to be 1 over 8 and then the square root of 1 minus, and then this x over 4 squared is going to be x squared over 16. Now if you look at what we need for the final answer, we need x squared here. We don't need a coefficient in front of the x squared, and at the moment we have this 16 here. So what we're going to do is we're going to write this as 1 over and then 8 and then the square root, and then we're going to factorize 1 over 16 out of this function inside the square root here to get rid of the 1 over 16 from this x squared. So it's going to be 1 over 16 like this here. Now if you factorize out 1 over 16 from 1, this is going to be 16, and it's going to be minus, and then if you factorize out 1 over 16 from this x squared over 16, this is now going to be x squared like this here. And then now we have this x squared here that we need in the final answer here. Now what we need to do now is we have this 1 over 16 that we don't want here. So if we take this out of the square root, so this is going to be 1 over, and then it's going to be 8, and then the square root of 1 over 16 is 1 over 4. So if we take this out of the square root like this here, and then this is the square root of 16 minus x squared, and we can simplify this because we can write this as 1 over, and then 8 times a quarter is equal to 2, and then this is the square root of 16 minus x squared like this here. And this is in this format here where a is equal to 2 and b is equal to 16, and this here is the final answer. Okay, so here's the final question in this video, where we're told a curve C is given by the equation sin x plus cos y is equal to 0.5, where x is more than or equal to minus pi over 2 and less than 3 pi over 2, and y is between minus pi and pi. And we're told a point P lies on C, and the tangent to C at the point P is parallel to the x-axis, and we need to find the exact coordinates of all possible points P, justifying our answer for 7 marks. So as this is worth 7 marks, it's obviously quite a difficult question to get and quite a long question to get all of the marks. Now this line here, we're told the tangent to C at the point P is parallel to the x-axis. So if we have the x-axis and if we have a line that is parallel to it, this means the gradient of this line is 0. So the tangent, the gradient of the tangent, is going to be 0. And remember a property of tangents, the gradient of a tangent at a particular point P is also going to be the gradient of the curve at this point P. So in other words, dy over dx, which is the gradient of the curve, is going to be equal to 0 at this point P. And this is useful to us because what we can do, this equation here, we can differentiate this in order to find dy over dx and then set it equal to 0, and then we can find the x and y values, and this is going to be for the point P. Okay, so we need to differentiate this equation here. Now as we have an equation that involves both x and y terms, the easiest way to differentiate this is using implicit differentiation. So to differentiate this, so let's differentiate both sides of this equation. So let's start with this side. Let's start with sin x. If we differentiate this in terms of x, this is just basic year 2 differentiation. If you differentiate sin x is equal to cos x, and then it's plus, and then if we differentiate cos y, now we need to differentiate this implicitly. Now, one thing I talked about in the implicit differentiation video is when you're differentiating y and you're differentiating it implicitly, you need to treat y as a function, and therefore we're going to use the chain rule to differentiate this. Now, I've talked about the chain rule already in this video, that the chain rule is equal to the inner function differentiated, and then this is multiplied by the outer function differentiated. Okay, so here we're trying to differentiate cos y. So as we're treating y as a function, we're going to say that the inner function here, y, this is the inner function, and we're going to say the outer function is cos here. We're going to say this is the outer function. So the chain rule is the inner function differentiated. So the inner function is y. So this is y differentiating. We talked about in the implicit differentiation video that when you differentiate y implicitly, it's equal to dy over dx, and then this is going to be multiplied by the outer function differentiated. So this is this cos differentiated, and when you differentiate cos, it's equal to minus sin, and then we're still going to have this y here that we don't touch, we just leave it as it is. So this is this side of the equation, sin x plus cos y differentiated here. Then this is going to be equal to, and if you differentiate 0.5, this is just a constant, it's going to be equal to 0. Okay, so we have this equation here. Now dy over dx is equal to 0, so if we sub this in, it's going to be cos x plus, and then dy over dx is 0, and this is times minus sin y, and this is equal to 0. So as we have this 0 times this minus sin y here, this term is going to cancel out and just leave us with cos x is equal to 0. So we need to find the values for where cos x is equal to 0 in this interval here between minus pi over 2 and 3 pi over 2. So the easiest way to do this is to draw a quick cos graph. So if we say that this is y and we say that this is x, so we need to do it between minus pi over 2 and 3 pi over 2. So if we draw it like this here, where we say that this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is minus pi over 2. So we're trying to find where cos x is equal to 0. So we can see that this is here, here, and it's also here as well, but we're told in this interval, so we're told x can be equal to minus pi over 2, which is this point here, but we're told that x cannot be equal to 3 pi over 2 with this inequality sign here. So therefore it's not going to be this value here, it's only going to be these two. So here we know now that x is equal to minus pi over 2 and pi over 2. So these are the two possible x values here. Okay, so these are the possible x coordinates. So in order to find the coordinates of P, we also need to find the y coordinates. And to do this, we can use this equation here, that sin x plus cos y is equal to 0.5. And what we can do is we can sub in these x values that we have into this equation and then rearrange in order to find y. And this will give us the coordinates for P, okay? So let's start with x is equal to minus pi over 2. So x is equal to minus pi over 2. So if we sub this into the equation that I just showed, so it's sin x, it's going to be sin of minus pi over 2, and then it's plus cos y, and this is equal to 0.5. Now sin of minus pi over 2 is equal to minus 1, so it's minus 1 plus cos y is equal to 0.5. If we move this minus 1 to the other side, we get that cos y is equal to 1.5. So we have to solve here for y. However, remember, for a cos graph, it doesn't matter what is inside the cos function. In this case, it's y. Remember that cos, the smallest value that it can have is minus 1, and the biggest value that it can have is 1. So here, this cos y is equal to 1.5. This isn't possible. Cos y cannot be equal to 1.5. It cannot be equal to a value more than 1 here. So therefore this isn't possible, so therefore here x cannot be equal to minus pi over 2 either, because it gives out this equation here that we can't solve. So there are no possible values for this point here where x is equal to minus pi over 2. Okay, so now let's consider the other possible x value where x can be equal to positive pi over 2. So x can be equal to pi over 2. So if we use the same equation, so it's going to be sin x, so it's sin pi over 2 plus cos y is equal to 0.5. So sin of pi over 2 is equal to 1, so it's 1 plus cos y is equal to 0.5. Move this 1 to the other side, so we get that cos y is equal to minus 0.5. So we need to solve this here. We need to solve for y when cos y is equal to minus 0.5. Now remember, the domain for y is between minus pi and pi. Don't get confused with the domain that we were using before with x. We're now talking about y, which is between minus pi and pi. So if we sketch a cos graph between minus pi and pi, so it's going to be like this here. I know that technically this should be the y-axis because we're trying to solve for y here, but it doesn't matter that much. So it's going to look something like this here, where this is 0, this is pi over 2, this is pi, this is minus pi over 2, and this is minus pi. And if we say that minus 0.5 is about here, we can see that in this interval there are two solutions here. If you take the inverse cos of minus 0.5, you put it into your calculator, it's equal to 2 pi over 3. And this is this solution here, this 2 pi over 3. Remember, cos is symmetrical around the y-axis, so this here is going to be minus 2 pi over 3. So there are two possible values for y here. Either y is equal to 2 pi over 3 or it's equal to minus 2 pi over 3, and both of these are for when x is equal to pi over 2. So therefore there are two possible coordinates for p. It's when x is equal to pi over 2 and y is equal to 2 pi over 3, or when x is equal to pi over 2 still, but y is equal to minus 2 pi over 3. And these here are the two possible points for p.